30 seconds of cold water on your skin triggers a neurochemical cascade that lasts up to 3 hours after you've dried off, put your clothes on, and started your day. You don't feel it happening. You feel what it produces, a particular quality of alertness, a low-level steadiness that doesn't come from caffeine and doesn't fade the same way. Most people credit the coffee. The coffee gets too much credit. Before we get into the mechanism, have you ever deliberately ended a shower cold, even once? Leave a yes or no in the comments below. Here's the simplest version of what's going on. Cold water touches your skin. Your body reads that as a signal. The signal travels inward, and what it triggers chemically, neurologically reshapes how your brain functions for the next 2 to 3 hours. That's it. That's the whole thing in one breath. Everything else is just learning to read the signal. Now let's actually read it. Your skin isn't just a surface. It contains millions of specialized ion channels, protein structures embedded in nerve cell membranes that exist for exactly one purpose: detecting cold. The specific channel responsible for mild to moderate cold is called TRPM8, which stands for Transient Receptor Potential Melastatin 8. It's the same channel that fires when you eat something minty. It's activated when skin temperature drops below roughly 28 degrees Celsius, which is well above what most people think of as cold. A cool shower, not an ice bath, is sufficient to open it. When TRPM8 opens, it allows positively charged ions to flood into the nerve cell, generating an electrical impulse. That impulse travels along sensory afferents, the incoming nerve fibers, toward the spinal cord, and up into the brainstem, specifically into a region called the nucleus tractus solitarius, which is the brainstem's central processing station for signals arriving from the body's periphery. Put simply, your skin fires a message, and the brainstem receives it within milliseconds. What happens at the brainstem is where things get interesting. That signal, or rather, the flood of simultaneous signals from thousands of cold-activated fibers across your skin, reaches a small, dense cluster of neurons called the locus coeruleus. It sits in the pons, the upper portion of the brainstem. It contains roughly 50,000 neurons, which is a tiny number in neural terms. But those 50,000 neurons project to virtually every region of the brain, and they produce almost all of the brain's norepinephrine. Norepinephrine, the brain's primary attention and arousal neurotransmitter, does something precise and underappreciated. It doesn't simply increase brain activity across the board. It improves the signal-to-noise ratio. Think of your brain as a room full of conversations. Norepinephrine turns down the background chatter and makes the conversation you're trying to have louder. Relevant signals become clearer. Irrelevant inputs get quieter. The technical term for this is increased gain in active neural circuits. The felt experience of it is focus, the specific kind that doesn't feel effortful. A 2000 study published in the European Journal of Applied Physiology by Sramek and colleagues measured plasma norepinephrine in subjects immersed in 14 degrees Celsius water for 1 hour. Norepinephrine increased by over 500% above baseline. 500%. And while a cold shower is considerably briefer than an hour-long immersion, the initial cold shock response, which is what drives the acute locus coeruleus activation, begins within seconds of contact and is disproportionately powerful in its first 2 minutes. Simultaneously, the same signal that activates the locus coeruleus travels along a parallel pathway to the hypothalamus, which triggers the adrenal medulla, the inner core of the adrenal glands, sitting just above your kidneys, to release epinephrine, the hormone most people call adrenaline, directly into the bloodstream. Heart rate climbs, blood pressure rises, breathing sharpens. These are the familiar sensations. The gasping, the involuntary sharpening of attention. Your sympathetic nervous system is treating this, correctly, as a controlled emergency. Here's the thing: what most people notice is the shock. What most people miss is what comes after it. The locus coeruleus, once activated by cold, doesn't simply fire a single burst and return to baseline. The noradrenergic signal persists, and that sustained norepinephrine output drives a second, slower cascade that involves dopamine, a neurotransmitter associated with motivation, reward processing, and the sense that effort feels worthwhile. The pathway runs through the ventral tegmental area, or VTA, a cluster of neurons in the midbrain that is the brain's primary dopamine production site, which receives input from the locus coeruleus. As norepinephrine drives elevated VTA firing, dopamine accumulates in the nucleus accumbens and the prefrontal cortex. The Sramek data showed dopamine increasing by 250% above baseline at 14 degrees Celsius immersion. That elevation, crucially, persists for 2 to 3 hours after the cold exposure ends. Two things make this different from other dopamine-raising experiences, and both matter. First, this is tonic dopamine, a sustained, gradual elevation of the baseline level sitting in the synapse rather than phasic dopamine, which is the sharp spike that occurs with reward events and which addictive substances drive to extremes. Phasic spikes produce the sharp reward signal. They also produce the crash, the craving, the tolerance that requires escalating doses. Tonic elevation produces something quieter and more useful, a sustained improvement in motivational state, without the receptor downregulation that would blunt the effect over time. Cold water, repeated, doesn't lose its potency. The mechanism doesn't habituate the way pharmacological stimulants do. Second, and this is the part the wellness industry consistently gets backwards, dopamine is not the molecule of pleasure, it's the molecule of wanting. It's what makes you willing to begin things, to sustain effort, to feel that tasks are approachable rather than inert. The steadiness people describe after a cold shower, the sense that the day feels manageable in a way it didn't 30 seconds earlier, isn't a mood lift in the conventional sense. It's a shift in motivational tone. The work hasn't changed. The brain's relationship to the work has. Honestly, the gap between what that mechanism is and what gets sold around it is something I find genuinely difficult to sit with. You'll find cold exposure bundled into protocols, stacked with supplements, marketed as the delivery vehicle for a dozen products that have nothing to do with it. The mechanism is free. It's in your shower. Nobody benefits commercially from explaining it clearly, so mostly nobody does. What the research doesn't yet confirm is how the response scales across age. The Sramek data and most of the replication work was conducted on younger adults, predominantly male. Whether the magnitude of norepinephrine and dopamine elevation holds at the same level in people over 60, or whether the time course of the effect changes, hasn't been tested at the same rigorous scale. The assumption has been extended to broader populations. The assumption hasn't been verified with the same quality of evidence. That's worth naming. Now, about cortisol, because this is where the mechanism gets genuinely counterintuitive. The initial cold shock triggers a cortisol spike. Cortisol, the body's primary stress hormone, rises sharply in the first minutes of cold exposure. If you stop the story there, you'd conclude that cold showers are bad for you in the same way chronic stress is bad for you. That conclusion would be wrong, and the reason it would be wrong tells you something important about how hormones work. The cortisol spike from acute cold exposure is brief and followed by a sustained suppression. Research cited in the Journal of Applied Physiology and reviewed through Stanford's Lifestyle Medicine group found that cortisol levels remained considerably lower than baseline for up to 3 hours following a 15-minute cold immersion at 10 degrees Celsius. The spike is the alarm. The suppression is the body recalibrating downward, a rebound into parasympathetic activity, the branch of the autonomic nervous system responsible for rest, digestion, and recovery. Your autonomic nervous system is in a constant negotiated balance between two modes: sympathetic, which mobilizes energy and attention, and parasympathetic, which restores and conserves. Most people in modern conditions spend the majority of their day tilted sympathetically, not in crisis, but chronically elevated. What cold exposure does, through its brief acute spike, followed by rapid parasympathetic rebound, is essentially force the system to exercise the full range of that negotiation. It's the autonomic equivalent of interval training. Heart rate variability, the variation in timing between consecutive heartbeats, which serves as a reliable proxy for autonomic flexibility, improves acutely following cold water immersion. Multiple studies, including work published in the American Journal of Physiology, have shown that cold immersion restores vagal-related heart rate variability indexes that had been suppressed by physical stress. The parasympathetic system, measured by HRV, is more active post-exposure than it was pre-exposure. The long-term picture follows the same logic. A 12-week study of participants engaging in cold water sessions 3 times per week found that by week 4, post-exposure cortisol levels had dropped significantly relative to baseline, and the trajectory continued downward through the remaining weeks. What's happening is adaptation, the same hormetic principle that governs exercise. A controlled stressor, applied repeatedly and with recovery, trains the system to handle the stressor with progressively less disruption. Your stress response becomes more efficient, not because it gets weaker, but because it learns to resolve faster. 3 or 4 cold endings per week, not every day, not once a month, appears to be where that adaptation curve bends most usefully, based on the 12-week study data. Recovery days matter. The adaptation is occurring in the refractory period, not during the exposure. Which brings us to what the mechanism actually tells you to do. Not a protocol, just the logical consequence of understanding what's happening. The signal that matters is the cold shock response, the initial activation of TRPM8 receptors, the cascade to the locus coeruleus, the norepinephrine and dopamine that follow. That signal requires the water to be genuinely cold, somewhere below 20 degrees Celsius, and it requires you not to fight it. The gasping reflex, the involuntary respiratory response, that's not a side effect of the mechanism. It's evidence the mechanism is running. Trying to suppress it by tensing against the cold blunts the signal. The biology responds to surrender faster than it responds to bracing. The duration that matters for the neurochemical payload is probably somewhere between 60 seconds and 3 minutes of genuine cold contact. Beyond that, diminishing returns set in on the acute catecholamine response. You're not chasing duration. You're triggering a threshold event. The body doesn't need to be deceived. It needs to be signaled. Temperature is one of the oldest signals it knows how to read. Now that you understand why the chemistry lasts 2 to 3 hours past the shower, there's a second half to this story. Click the video on screen to find out why walking barefooted on grass feels weirdly good. The next time you reach for the cold tap, you're not doing a wellness practice. You're activating a sensory channel in your skin that reports to your brainstem, which reports to a 50,000 neuron nucleus that talks to almost every region of your brain simultaneously. The steadiness you feel afterward, that's not the cold wearing off. That's the chemistry running exactly as designed. You just finally know what's running it.